we are going to look at the rational numbers and their decimal expansions. Okay, we have a theorem here which tells that any rational number is being represented by P by Q, and if this Q here, if it can be factorized as 2 power n and 5 power m, then this number is going to have a definite number of, it's not going to be continuous, it's going to have definite, it's very definite number. Okay, let us look at it with more examples. Shall we go to the exercise directly? Now, exercise 1.4. First question, 13 by 3125. By now you will be remembering the prime factorization method very well, right? So I am doing that again. 3125 divided by 5. This number ends with 5, so I am continuing with dividing with 5. 6 times, and I have remainder 1. 12, 2 times, 2, 25. So 5. Again I am going for 5 with 5. 1 time, remainder 2 times, 25, 5. Again with 5, 2 times, 25, 5. 5 and 5. So this number can be written as 5 power 5. 1, 2, 3, 4, 5. 5 power 5. So 3125 can be written as 5 power 5. I said Q should be, it should be possible for us to write it in the form of 2 power n, 5 power m. Okay. So we are able to write this number as 5 power 5. So it has 5 power m here. So we can say that this number, this division will give a perfect rational number as a end result. That's all. Without dividing, I can predict the answer that this number we can give a, that's the question, right? It is giving a terminating decimal as an answer. Okay. It just give. Okay. The next sum. First sum. This is the second sum in it. 17 divided by 8, and in this I am dividing, doing prime factorization for the denominator 8, and I do it for 2 times with 2 table. Again I can write this number as 2 power 3. Again I have got this part of in the answer. So this fraction also is going to give a definite result. It's not going to be a non-terminating decimal fraction. Okay. The next sum, 64 by 455. Okay. I am going to do prime factorization for 455 with 5 table, 9 and 1, and again I am using 7 table here. 1 time, remainder 2, 21, and that comes for 3 times. So this number can be written as 455 can be written as 5 into 7 into 13. Even though I have 5 here, I have got 7 and 13. And because of these two numbers, these two factors, this number is going to give a non-terminating decimal fraction. Okay, this number is going to give a non-terminating. These two have got 5 powers and 2 powers here. But here we have got other new prime numbers 7 and 13. Because of that reason, this is going to give a non-terminating decimal fraction. The next sum, 15 by 1600. Again I am dividing, doing L division for 1600 with 2 table. I get 800. Again with 2 table, 400, again with 2, 200, again with 2, 100, again with 2, 50, again with 2, I get 25, and again I do with 5 table now. So what's the answer? 1, 2, 3, 4, 5, 6. So the answer is 2 power 6 into 5 power 2, and this is a best example to have an expression like for this 2 power n and 5 power 2. It has got both the factors, and so this question is going to give an exact decimal fraction as a end result. Okay. fifth sum. (29 by 343). Okay. Again, I am going to take the remainder denominator alone. 343 divided by what number can it be possible? What do you think now? Okay.
Don't tell all these things on video, Vitas.
We'll use the 7 table here. Okay. Four
Tell
times.
I just spoke. So you should repeat it again. No, that doesn't mean you stop. You just go there and then you tell them, like, we're going to be doing this some right now, and you start. Saw my leopard spots, sir. I put black.
போட்ட உடனே நினைச்சேன் அது leopard இருக்குது அந்த இவர் டாக்டர் சொன்னார் ஒரு தடவை அவருக்கு நம்ம நெய் பாலிஷ் டாட்டா டாஸ்ட் பேர் எல்லோ black டாட்ஸ் அப்போ சொன்னார் சச்சின் இது புளி கறிங்க அப்படின்ட்டார். Okay, we'll come back to the sum now. The fifth sum, 29 by 343. I am considering the denominator 343. I am dividing it with 7. Okay, so when I consider with 7, 4 times 28, and I have get a remainder 53. 53 is for 7, 8, 49. Okay. And again 63, so 49, and again I do with 7 table, and so I got this. So 343 can be said as 7 power 3. We don't have the factor prime factor 2 or prime factor 5. So this number is going to give surely a recurring decimal and the answer. Okay, the next sum. They are given the answers directly actually in this sum. 23, sixth sum, 23 by 2 power 7, 2 power 3 sorry, and 5 power 2. The question is very direct. We don't even do this prime factorization. Yeah, they are given a direct answer. 2 power 3 and 5 power 2. So we can definitely say that it is going to give a definite proper decimal answer, terminating decimal answer. The next sum, seventh sum, 129 by 2 power 5, 2 power 2, 5 power 7 and 7 power 5. Again, we have got a 7 here, but we require only 2 power n and 5 power m. Even though we have 2 power 2 and 5 power 7, because of the 7 as a factor, this is not going to give a proper answer. It is going to be a non-terminating decimal. Okay. The next sum, 6 power 6 by 15. 6 by 15. And again, I will do L division for 15. It comes for 3 times and 5 times. 3 and 5, even though I have 5 here, I don't have 2 here. Because of that reason, it has 5 here mainly, and because of that reason, this is going to give a definite decimal fraction. It doesn't have 7. That is the main important factor, and because of that, we are going to have a definite decimal as a end result. The next is a 35 by 50. And I'll do L division for 50. I'm using 5 table first. 10, I get 2 and 5 again. And now this is 2 power 1, 5 power 2. And again, this is a best example for the required cube format of cube. And due to that, this is going to have a terminating decimal. This is going to give a terminating decimal as a end result. And the next sum, 10th sum, 77 by 210. And this, when I am going to do prime factorization for 210, I will do with 7 table first, 3 times, and 3, 10, 2 and 5. Even though I have a common number of 2 and 5, I have 7 also along with it. And because for that reason, it is going to be non-terminating decimal. Okay. So now we have finished all the sums in the first question, and to mark it, I can say that the first sum, second sum, fourth, sixth, eighth and ninth are all giving a definite terminating decimal as an answer, and the second sum is dependent on it. So for that reason I have given it. Okay, you can just mark it in your book also. The first, second, fourth, sixth, eighth and ninth sum all are having giving a terminating decimal as a result. And now we are going to prove that the second question they are asking you to prove that it is giving a terminating decimal as a result. Okay, they have to divide and prove it. Okay.
Bad dude, you're very quick.
So we come do the second sum, the first question. I have to prove by dividing, I have to prove that this number is going to be giving a terminating decimal. Okay. The second sum, first question. 13 by 3125. When I divide this, 13 divided by, first I have to have 4 digits I will raise. So first I keep a point decimal there. Then I can add any number of zeros. Once I keep a point decimal, I can have any number of zeros. So first I consider the first 0. Is it possible to divide? No, it's not possible. So I add a 0. I consider the next 0 along with it. Is it possible to divide? Even now, even though it is 4 digit number, it's smaller than this number. I can't divide, so I add one more 0. Okay. So the next 0 I consider. So now for this number, I have already done it. When I use 4, I get 12,500. When I subtract, I have 500. And I bring the next 0 down and I get it for one time. 3,125. When I subtract 5, 7, 8 and I can bring one more 0. As any number of zeros can be added, I bring one more 0 down. And this comes for 6 times 750. Okay, so it has ended and it has given a definite result. This is why even without doing such a big division, we can say we have done it in the first earlier sum. When it has a denominator of 2 power n and 5 power m, this is going to give a definite decimal as a result. Okay. The next sum is the second sum, 17 by 8. Second sum, 17 by 8. I'll divide 17 by 8. I'll do it for 2 times directly, 16. 17 by 8, yeah. Then I get a remainder 1. I keep a point, 0. 1 time, 8, 2, 0, and I can't divide it again. It goes in for 2 times, 16. I get a remainder 4, and it comes with 5. Okay, so this also I have got a terminating decimal as an end result of the 17 by 8. And to remember back, we are told 8 is equal to 2 power 3. So it was in the format of 2 power n and 5 power m. Here 5 power m was in the format of 5 power 0. So it had 2 power n. For that reason, it has got a terminating decimal as the end result. Then going forward with the fourth sum. Fourth sum. Something is wrong with my pen. It's okay. Fourth sum. By 1600. Okay, so I'm going to use divide 15 divided by 1600. Again, it has got only 2 digits, so the beginning itself I keep a point and I can add n number of zeros. Okay, when I keep a point, I can add n number of zeros, and when I divide, first I consider the first zero. It's not possible to divide, so I add a 0 in the new on the top. And I consider the next 0, even then I can't divide, so I'm adding a 0 on the top. So I consider all the 3 zeros, and it comes for 9 times, and it sums up to 4, 0, 0. So when I subtract 6, that's it, and one more 0 I'm bringing from the middle. And when I divide again, it comes for 3 times 1800. 0, 0, remainder 2, and here 1. And I bring one more 0 from, and it comes for 7 times 1, 2, 0, 0. And I have one more 0, and it comes for 5 times 8000, and it's O. So again we have got a terminating decimal expression. The next sum, 15 by, the next sum is 23 by 2 power 3. So 23 by 2 power 3, 5 power 2. Okay, so during the earlier sum it was easy when they are given it directly like this. Here it's not difficult again, we have to multiply it. So 23 by 2 power 3 is 8 into 5 is 25. 8 into 25 is 200. 23 by 200. I'm going to divide 23 by 200 now. And it has got only two digits there, so we have to keep a point in the beginning only. One time 200, and I bring 1 0 from the one time again 200, and 0, it comes with 5 times. That's it. So again it's a terminating decimal. The next is a 6 by 15. 6 divided by 15, it's a smaller number, so I keep it decimal in the beginning only, and it comes for 4 times. That's it. So again that's a terminating decimal. And the next sum, 45 by 50. Shall we do a different logic instead of doing the same thing again and again? Let us follow a different logic. Okay. This is the last sum. And by now everyone will be very sure and thorough that if the denominator is going to be 10, we are going to keep a point. And if the denominator has got 100, we are going to keep the decimal with 2 points, right? So I am going to convert 50 into 100. It's very easy now. So I am doing that method. Okay. So when I multiply into 2, the numerator becomes 70 and the denominator becomes 100. The numerator and denominator, if they are going to be multiplied with the same number, the value doesn't change. I am using that logic, and so I multiplied the numerator and denominator with 2 and I got 70 by 100, and now the denominator has got 2 zeros, 100, 2 zeros. So directly I can keep a point like this, that's all. So this is also having a terminating decimal. And the next sum, third sum, it's interesting. They are given a very long number and they are going to ask, and they are asking us, they are given us a long, in the third sum, they are given us a long, all the three sums, they are given a rational number. We have to define whether it's rational or not. So we have to show that it's P by Q. Is it possible to write it as P by Q? And by that we are going to say whether it's a rational number or not. So the first sum is 43.1, 2, 3, 4, 5, 6, 7, 8, 9. We have got a definite decimal. Okay. So this number can be written as 43, 1, 2, 3, 4, 5, 6, 7, 8, 9 by, I remove the point. So I put a 1 and I have added, how many digits were there? 9 digits were there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have represented it in the form of A by B. If any number can be written as A by B, and if the denominator is not equal to 0, automatically the number becomes a rational number. By that logic, this number is a rational number. Okay. And again, this number can be represented in the form of 2 power n and 5 power m. This big one with so many zeros, surely it will have factors of 2 power n and 5 power m. And by that reason, this is going to have a terminating decimal as an end result. Okay. Then the second sum, 0.120, 1200, 1200, 12000. Okay. So this is the second sum given, and this number, they are saying this number is not terminating. When it's not terminating, what happens? We cannot have a proper definite denominator. When we are not able to have a proper definite denominator, it cannot be written in the form of A by B or P by Q, and by that reason this becomes a irrational number. And again, this number is not having the same numbers, it's not getting repeated again. If it is 120, 120 repeated again, then at least we can say it is a irrational number. It is a rational number, but we can say it is a repetitive rational number. Non-terminating rational number at least. But now, as these numbers are not going to be the same, it's not same, so it is a irrational number. Irrational number, as it cannot be written, in the format of, A by B. Okay. And then the third sum, 3.123456789, and the line above says that it is terminating. It's terminating there. No, it's non-terminating, but the same thing is getting repeated again and again. The same decimals are getting repeated again. Okay. So how are we going to do this? Again, this number also, it is non-terminating, but it is a rational number. Okay, it's non-terminating. I told the line above represents it's non-terminating, but it is rational. The number is non-terminating, but rational. Okay, it's not a rational number, but rational, and it cannot be written. It can be written as P by Q. It can be written as represented as P by Q, but the only point is, but Q is not, we cannot factorize Q as 2 power n and 5 power m, and because of this reason this is non-terminating and it keeps on going. That's it. So this is the way we are going to tell whether this number is giving a terminating result or non-terminating decimal. That's it. That's the end of irrational numbers.
Yeah.